Well, good afternoon, Calc 3 class. Hope this video finds you guys doing well. It's Thursday afternoon, April 9th. My family as well. We're getting ready to celebrate Monday, Thursday tonight. Ever since my son was born about 8 years ago, we've always had a kind of a special lamb dinner, and we read some different passages from the scriptures and just have a good time remembering what Easter is all about. So we're looking forward to that. We're healthy and well, and hope you are the same. I did post a little post on Teams just asking how you're all doing. Would love to hear from you guys. Just want to touch base, just make sure you're doing okay, both in general but also with the course. It's kind of strange. I don't have any feedback on how you're doing with the material and if you're able to digest it. So if you guys could comment on that thread, that would be great. You can also send me a message one-on-one as well if you're having trouble. So, well, let's dive into 12.7. Spherical coordinates. This won't be nearly as long as 12.5 was, so that's good. So we're going to learn another coordinate system. So we have the Cartesian coordinates, the standard x, y, z coordinate system. Then we learned cylindrical coordinates, and that was basically polar plus the z-axis, which we mentioned you can actually do cylindrical around other axes as well. I keep mentioning that because some of you are going to notice a situation where you're going to want to do that, and when that day comes, I want you to know that you can. So today we're going to learn about spherical coordinates, and let me just introduce you to the coordinate system, and then we'll see why they're useful to us. So it's kind of fun. So we're going to pick up a point right here in 3 space, and I want to show you how we can describe this point in spherical coordinates. So we're going to, let's go ahead and drop our vertical down to the xy plane, and then I want to go ahead and drop a line out. This is my x-axis, my y-axis, and my z-axis. So let me begin with what's familiar. So theta, this angle right here, is the same theta you've learned in polar and cylindrical. It's the angle off of the positive x-axis. That's the same. But now we're going to have another angle and another measurement. So in both polar and cylindrical, you labeled this, let me get my marker up, my highlighter, you labeled this distance right here was your rho. All right, well, or your r. Well, that's going to change now. So I'm not going to be interested in this distance. I'm going to be interested in this distance, the distance from the origin itself to my point. And instead of calling that r, I'm going to call that distance the Greek letter rho. Yes, it looks just like a p. You can call it p if you want to, but it's really rho. And then that's not quite enough to capture this point because we also need the angle off of the positive z-axis. And so this angle coming down off the positive z-axis is angle phi. So in spherical coordinates, this point would be the point rho, comma, theta, comma, phi. Rho goes first, then theta, then phi. All right, so a couple of things to note. First off, rho has to be positive. Can't have a negative distance from the origin. You actually could make sense of negative rhos, but we're going to keep rho positive. Second off, my theta is just like before, and it can swing all the way around from 0 to 2 pi. So your theta can go all the way around just like before. But now the question is, how do I get points in 3 space whose z value is negative? What if I want to get a point down here somewhere? And that's fine, we can do that. You do that with phi actually, but I want you to realize that phi is always between 0 and pi, not 2 pi. I don't want my angle phi to swing all the way back around. Otherwise, I could get to the same point 2 different ways. I could spin around this way, or I could come down through phi. So we limit phi. The most you can do is swing down to the negative z-axis, and then if you want to get over there, you spin theta around. Does that make sense? So if I want to get to this point over here, where we're actually down and then over like that, the first thing that I would do is swing my phi down, and then I would swing theta around to pick it up. So that is how spherical coordinates work. Those are the important bounds that we need to be aware of for spherical coordinates. Another thing you might want to know is how do you convert from Cartesian to spherical? Well, let's write it down. So, So let's write that down. So here we go. X is rho sine phi cosine theta. Notice you're familiar with the r cosine theta. That's the same. We just throw in a sine phi. Y is going to be rho sine phi sine theta. You're used to thinking about y as r sine theta. So again, throw in a sine phi in both of those. What's z? Z is just rho cosine phi. So that's the conversion when you want to convert to from Cartesian to spherical coordinates. And we should also mention that it follows from what we just wrote that x squared plus y squared plus z squared. If you plug it in and play with the trig identities, you're actually going to get rho squared, and you should recognize this as the equation of a sphere. So this is sort of why they're called spherical coordinates. We'll play with it in a minute. They make graphing spheres really easy. I had left a spot to write down what the rho and the phi and the theta were, so maybe let's do that just for the completeness sake of the notes. I've said it already. Rho is just the distance from the point, from the, let's say from the origin to the point, and then theta is the same angle as polar slash cylindrical, and then phi is the angle between, let's call this point 0, and then let's call this point A, and O is the origin. So it's the angle between the positive z-axis and the line, the way that I've written it would be OA, that line. And we've already given the bounds on that. All right, I think we've got everything a little out of order there, sorry. So we've introduced the system, we've talked about how it works, we've made clear the bounds, the restrictions on rho, theta, and phi, and then we've also jotted down how you can convert from Cartesian to spherical. So let's stop this video here. And in the next video, we'll practice just a couple of really basic graphs in spherical, and then we'll learn how we can set up triple integrals in spherical coordinates and use this to make our